All right, now we're going to load in a pre-built model. So essentially what was done here was I took the same data that you just loaded. So the same faces, the same training data set, everything was identical. Even the code was identical, except for I saved the best network as opposed to just the last one that was run. And I ran this on a computer with a GPU, and I ran it for about 30 hours or so. Now, this will be a much better model than what you were able to produce simply because I had a lot more computational capabilities at my fingertips. However, it will still be fundamentally limited because we're using a ResNet 18. So the type of model that we built here is not necessarily, it's not a very deep network, first of all, and it's also not necessarily the best network for this type of a problem. Rather, it's a network that can be fit reasonably quickly. So to load in the model parameters that are better, we're going to do the exact same thing that you already did here, where we did the load state torch load bestmodel.torch. However, we're going to download something to define bestmodel.torch. So first I'm going to go ahead and go all the way back to the top of our code. So this is the first bit of code that we ran in this lab right here. And this was just the code that we used to download the faces. We're going to do the same thing, but we're going to actually download the information about the neural network in this particular case. So I'm going to get rid of the faces link. Obviously, we won't be downloading those again. I'm just going to copy and paste this. So this is available on the website, this URL. You can also just type this in directly. And I'm going to save this here. For the sake of all of our sanity, I'm going to call it the same thing. All right, so we'll go ahead and run this. And there we go. So we've now downloaded that file, and we can now use this file to parameterize our network. So to do that, we're going to use the exact same code that we used to load this. So you'll recall bestmodel.torch. That was your individual best model. All we're going to do is replace this with the Cyclone best model. And this is just the best model that we fit on our on the more powerful HPC. And then all we should have to do is run this. Now, because it's likely that fitting your model took a very long time, you may have returned to scikit after a little while. It's helpful if we put all of this in a new snippet. So we're going to build our new model in a new snippet, and we probably want to redefine our imports so that these models work. So we'll go up to where we defined our earlier model right here, and I'm just going to copy all of these imports. I'm going to put them down here. Now, you don't have to do this necessarily. This is just for convenience so that I don't have to worry about having everything imported correctly within this snippet. All right, and there we go. So we have all keys matched successfully. You'll recall this is exactly the same thing happened that loaded your model. So for example, if we wanted to compare your model to the best model I was able to achieve on Cyclone, you would just delete this Cyclone. You still have bestmodel.torch, which is what you named yours. If you named it something else, it may need to be something else. And then we can run this. So now, all keys will still match successfully. It's just from your model instead of mine. So it's just loading in the parameterizations you found. I'm going to go back to Cyclone, and we'll go ahead and run this. And there we go. So we now have this parameterization done. We can now do these same predictions that we did before, but using the best parameterizations that were found here. So let's go ahead and go up, and we'll do a random set. So let's just take this for an example. And again, so here we have our prediction model. It's now loaded based on these. And then everything else should be exactly the same. We're just going to do this prediction based on a different prediction model, which is now this model. We do have to define our image transformations first. So go make sure you copy and paste this. I copy and pasted this from just above a little bit when we had defined our image trans right here. So we do have to apply those same transformations, the biggest one being putting our images onto tensors. So with that, this should now run. All right, so this one, we have we don't think that these are twins, right? A 51% chance that these are not twins. So this one was correct. There you go. Again, this one is correct. Let's run another one. This one is slightly wrong. So we barely would predict that these two are similar, but not by a very big margin. This one we get wrong. We do predict that these are closer to twins. So about 80% of the time, if I were to run this 100 times, 80 of those we would get right. 80% of these we are able to classify correctly. This one is a very correct one. These are definitely not twins. But then there's still 20% that we are going to get wrong. So 2 out of 10 we are going to get incorrect. Now let's take a quick look at the twins. So the exact same code, but we'll look at the twins instead of diff. So I'll copy this, paste it here. We'll just change this to twins. Now let's take a quick look. Okay, so this one we are predicting they are twins. This one was easy because it's the same thing. Twins again. Here we go. So two different pictures of the same person. We would still predict that this was twins, even though it's a different image. We are predicting these are twins, even though it's two very different images of Oprah. So you can see that this particular model parameterization is doing a pretty good job, right? We are predicting these are twins, and these are truly twins, even though they look very different, at least to me visually. And so we're doing a pretty good job on this overall calibration. Let's see if we can find one that is incorrectly classifying these as not twins. This is correct. This is twins. Here we go. And so this is an example of one where, for whatever reason, we are classifying these incorrectly. We're saying these are not twins, despite the fact that they are. So now what we actually want to do is we're going to use this model to try to identify from a haystack of potential matches the correct match. So this is on the back end how an algorithm might work that looks through camera footage to find out if someone of interest is walking through a room. This is not the computationally efficient way to do that, but this gets you at the base logic of how it works. So just as an example, let's kind of pick a case that we want to search for. So in this particular case, I'm going to pick a image of Halle Berry. So we'll use this image. So we'll be wanting to search through our image, our faces, to try to find out who this is, right? Imagine you have a picture of this and you don't know who it is, and you want to use your convolutional neural network to identify that. So this is kind of the simple example that we're going to be using. You could also use this, for example, to put a picture of yourself into this script just by uploading it through Jupyter, and you could see which one of these celebrities you look the most like, at least according to the convolutional neural net. So let's go ahead and write this code. It's mostly going to be copying code from before, where we'll be looping through every single possible match with Halle Berry, and then trying to identify kind of the images that she is most similar to. So let's go ahead and we're going to do a bunch of imports. So this is just copy and pasted imports from earlier. And then here, this is the defined path of the image. So we're trying to identify this particular image of Halle Berry. Now I'm going to write a little bit of new code. All right, so I'm going to pause here for a moment and walk through exactly what's happening in the code so far. This is very similar to what we've done before, so there's not a whole lot of difference in terms of the types of things that we've done before this moment. First and foremost, we're creating a new directory just called FaceMatch. You can call this whatever you want. So I'm making this directory FaceMatch. Note you may have to run this first for the first time you run this code, because it's going to try to delete a folder that doesn't exist. I do like to create a temporary folder here that we can dump pictures into. We're going to count how many faces we want to compare it to. And so right now what we're doing is we're looping over all of the different folders in LFWs. This is all those different faces that we had selected before. And we are going through, and we are, the same as we did before, we're limiting to only 5 files, and then we're looping through all the images to create matches where one of those 2 images is always our image to identify. That is the picture of Halle Berry. Importantly, I am also including this if random.random equals 0.999. Effectively, we're only going to take a small subset of our images so that this exercise can run in a reasonable period of time. What we're going to add next is we're going to create one image that is the true image. It's going to be a match of Halle Berry. Everything else that we're generating is effectively going to be the images that we're using to try to trick the algorithm. So I'm going to go ahead and do that now. All right, so I'm going to go ahead and run this. What I just did here was I'm creating a single image that is going to be our target image. That is this image we're trying to identify. and an image I know to be of Halle Berry. This is going to be an image that we didn't include in our calibration. This is image 7, not image 1, 2, 3, 4, or 5. So this should be at least reasonably challenging for the algorithm. And so I'm going to add that to the list of all of the twins that I'm creating that are just twins that are likely not Halle Berry. And we'll see kind of how this, we'll show an example of this in just a moment. I'm going to go ahead and run. This will take just a second to run, not too long. Briefly, I'm going to type. I'm going to type this right here. For now, I'm going to delete it in just a moment. Just the first time this runs, you do need that folder face match to already exist. Okay, and that's already run. So let's take a look at what we've got here. So we can type in Jupyter !ls, and then we'll do / face match, and take a look at what we've got. Here we go. So in this particular case, we created 1, 2, 3, 4 images that are not twins, and then one that is the true twin. So this for loop here created the first 4 files, 0.jpg, 1.jpg, 2.jpg, 3.jpg, and then this code down here created the true match.jpg. So this folder has basically 4 that are wrong and 1 that is right. So let's just take a look at kind of what this looks like. So let's do a test image. Here we go. So this is one example of something that we know is wrong. We'll do another example of something we know is wrong. Right. So these are all cases 1, 2, 3, and 1, 0, 1, 2, and 3 are all. That's how I feel right now. They're all cases where we know we're wrong. And then true match is the match that we created that we know is correct. Right. So this is where we want to write an algorithm that knows across these, in this case, just these 5 cases, that this is the right one. In this algorithm, we should get it right. The guess that we have for Halle Berry should be either the top guess or the second from top guessed, because we only have 5 cases and we know our algorithm is about 80% accurate. So normally, like on average, we would expect to find Halle Berry's face with a pretty decent degree of accuracy in this scale of a problem, which is a pretty small scale problem. But let's go ahead and see what that looks like. So first we can look at just kind of an example case of one of these and do the comparison. So let's do that first. All right, and here we go. So in this particular case, we would have a similarity score of 0.691. So we would consider these as potentially twins if we were just looking at the binary. However, what I'll be curious to look at now is how these compare relative to one another. So we have face 2. Let's look at face 1 and see what that score is. Is it 0.73? Let's look at 0. A 0.55. So the right now the first, so 0 is 0.55. We look at 1, 0.73. Look at 2, 0.69. So 1 is better than 2. Look at 3, a 0.81. So this is the best match so far. And then let's look at the true match. And that's a little bit worse. So this, I think the true match in this case would be ranked second. All we want to do here is write an algorithm that does what I just did automatically, very quickly, doing all of those comparisons to see where this image ranked. And hopefully it's at least like second best in this particular case. So to do this, we want to extract just this number. This is the number that we will treat as our similarity score. And to do that, you just have to do this. Now, this looks really complicated. And the reason that we can't just simply do this as we would normally do is because this is still information that is held within a tensor. So we actually need to move that data off of a tensor into a normal type of array that we can manipulate. So that's what this code does. Don't worry too much about what's going on under the hood here. Just be aware that we're effectively converting a tensor into something we can manipulate in a normal NumPy array. And now when we run this, instead of 0.7641 being a part of a tensor, we should just get the number 0.764, which we will interpret as the similarity score. And there we go. So now we just have that one value. So now we're just going to write a loop that goes through and does this for every single image in our face match folder. So let's go down here and write that loop. This will almost universally be copying and pasting from earlier things that we have done, where we're going to build this final model. So first I'm going to copy all of our imports just so that we have them on hand. Okay, next we just want to create an array that tracks our similarities. So we'll just define an empty array. Now we have to define our image transformation, just like we did before. So we'll go up here and we'll copy our image transformation right here. And now we're going to write a for loop that just goes through, again, every folder in this directory. So every file that's in the face match directory, we're going to loop over and calculate that similarity score. So let's go ahead and write that code. Okay, and here we go. So this is all the loop is. We're going to loop over every file, and then we're saving. You'll remember the pred.softmax.data.cpu.numpy. This is just the exact same thing that we put right here. So it's extracting the similarity score. And then we'll just go ahead and run this, and this will give us a new kind of a new file, a new pandas data frame that tells us the similarities of every single file. And this should be very quick because we're only running the prediction in this particular case over 5 different files. Here we go. So this is the total similarities and the matches. What we actually want to do is sort this by similarity, right? We just want to have the top ones at the top. So that's fairly simple because this is a data frame. We'll do this. And there we go. So now it's sorted. So we do see the true match in this case was the second best, which is roughly in line with what we would expect from this particular model. This model is, again, between, I think it was 75 and 80% accurate. So we're not going to get the right answer every time, but we should expect the right answer to be of the kind of better set. If we had more time, more computation, a deeper model, all sorts of things, we could probably get this, we could definitely get this to be the best match every single time. So you'll note, first and foremost, this prediction step doesn't take very long. Even for those 6 images, it was, nearly instantaneous. As we increase the number of images, it will take longer. This is a pretty easy problem because there's only 6 things to search through in our haystack. For bigger problems, we will want to have, this will take, upwards of 10, 15 minutes to run. So we're going to do that, but before we do that, we want to provide some information that is printed out that tells us how far through our data set we are, how many faces we've processed, so we know how much longer roughly we're going to need to wait. So to do that, we're going to directly to the standard out. There we go. And you'll see very quickly this just flew through what file we are processing and how many more we have remaining. And add one more space in here just to make it look a little bit nicer after the file. And there we go. So now let's turn this up a little bit. Let's make this a little bit harder for our model to do. So the parameter that controls this is here, this random.random. This says what the % chance is that we'll write something out to our faces folder. Let's just turn this down a little tiny bit more. So we'll set this up to like 0.995, and this will give us more faces in our haystack that we're searching through. So I'm going to run this. Let's take a look at the folder. And there we go. So now you can see we have many more faces that we have to search through. It's still not a huge number of faces, but a lot more. We still have the same true match. So that hasn't changed any. Now we're just going to contrast these similarities across all of these images. So let's go ahead and run that now. And you will see this now is slowly incrementing. All right, there we go. And now we can look at this list right here. And you can see in this particular case, our true match is all the way down here. So this is out of the 50 odd files that the 49 files we just processed. This is roughly in the top, I can't quite tell, let's call it the top 15, which again is roughly in line with what we might expect. We are going to expect a reasonable amount of error in this model, though it is nice to see that this is at least, in the upper half. We can do this with as many faces as we want. This is just one more example where we have the true match again. This time it's ranked 5th out of all of our different observations, so all 17. So that gives us an overall accuracy in this particular case of divided by 17. So we were worried about the 70th percent in this particular case, which isn't terrible. I mean, that's roughly in line with what our model might expect. So that's it for convolutional neural nets. I highly encourage you to play around, see if you can fit a better model than what I was able to accomplish by changing things like the architecture of your model. You can always look into different ResNets, different sizes of ResNets. There's a lot of different options for how you can try to beat this out. Hope you enjoyed learning about convolutional neural networks, and I will see you next time. All right, let's see here. Full and full and full 43% similar to Halle Berry. Weird. And full 79. 294. Who's 294? Let's see. Mr. 294. Alright, 294. Wonder who that is. 294. Paul McCartney. Interesting. Yeah.